Rational functions part 2. I want to focus on intercepts here. So I want to look at the vertical asymptote, the horizontal asymptote, holes, intercepts, x-intercept, y-intercept. So I'm going to do 3 different examples, 3 different functions, and I'm just going to look at their graphs and different parts of their graph. So the first thing I want to look at is the vertical asymptote, which I talked about in the last video. That's where this function is undefined. So what value can I not plug in here? And so this particular one is x equals negative 2/3. Because if you plug in negative 2/3 here and you multiply, the 3's will cancel and you'll end up with negative 2 plus 2. And so there's a vertical asymptote there. So let me just try to sketch this a little bit. So you have a vertical asymptote at negative 2/3, which is about right here. This is just rough sketches that I'm doing. You have a horizontal asymptote. As I said in the last video, I look at the exponential value of the numerator and the denominator. This one is greater than this one, therefore x equals 0, which is the axis here, is a horizontal asymptote. Actually, it's y equals 0, not x equals 0. Y equals 0 all the time. So right here we have a horizontal asymptote. Now I want to look at a hole, but there is no hole in this particular example because holes occur when you can't plug a number in and then suddenly you can after you've reduced it, but I can't reduce this function. It's as reduced as it can be. So there is no hole in this particular graph. The y-intercepts occur when x is 0. Y-intercept is something that crosses here. So the only way it can cross here is if your x value is 0. Oops, I put that in the wrong place. X is 0. So if x is 0, you just plug in x equals 0, which gives you 3 times 0 plus 2, so it's 5 over 2. So the y-intercept is 0, 5 over 2, which is 2.5. So it's 0, 2.5, 1, 2, 3, 2.5. You have an x-intercept right here. I'm sorry, a y-intercept right here. And then x-intercepts occur when y equals 0. And so you want to set y equal to 0. The only way y can ever equal 0 is if the numerator of this fraction equals 0, because 0 divided by anything equals 0. And this will never be 0 because there's no variable here. This is a constant. So that means that there is no x-intercept, which makes sense because you have this horizontal asymptote here. So there is no x-intercept. Okay, so the graph basically looks like this, and you can figure this out by plugging in a couple more points. But you have the intercept here, you see the asymptote here and an asymptote here. And then over here we could plug in, let's say we plug in negative 2 into this function. We would get negative 6 plus 2 is negative 4. So you'd have negative 5/4, which is like negative, well, it's negative. That's all we really need to know. So the graph is down here going like this. Again, you could plug in a bunch more numbers, but you have these 2 asymptotes. Okay, so that's basically what the graph looks like, and this is what I'm concerned with, your ability to find the vertical asymptote, the horizontal asymptote, the hole, the x, and the y-intercept. So I want to look at 3 examples in this video. My next example is y equals negative 3x plus 3 over x squared minus 6x plus 5. I can factor that. If I factor out a negative 3 in the numerator, I get x minus 1. If I factor the denominator, I get an x minus 1, which ends up canceling, and I get x minus 5. And you can see that 5 times 1 is 5. Negative 5 plus 1, negative 1 is negative 6. Okay, so it looks like in this function you cannot plug in x equals 5 and x equals 1 because you'll get zeros in the denominator. But once you reduce this, you then get a new function, which is equivalent to the original function. And now you can't plug in x equals 5. So the fact that you could never plug in x equals 5, that's a vertical asymptote at x equals 5. The horizontal asymptote occurs, we go back and we look and see that, again, this exponential value in the denominator is greater, so it occurs at y equals 0. So once again, you're getting something that has a horizontal here and 1, 2, 3, 4, 5, a vertical here at x equals 5. The hole, this one does have a hole. The hole occurs when you cannot plug in x equals 1 into the original function. So the hole occurs at x equals 1, and more specifically, when x equals 1, you can now plug in 1. 1 minus 5 is -4, so you get -3 over -4, or 3/4. So there's a hole at 1 3/4, which 3/4 is about right there. So there's your hole. Then we look for the y-intercept. Y-intercept occurs when x equals 0. So just make x equals 0 here, and you get 3/5. So at 0 3/5, which is about here, you have a y-intercept. So this graph is going like this. And your x-intercept, once again, you don't have one because that's when y equals 0, and y will never equal 0 because this is a constant number here, and you can't. The only way you get 0 is when you divide 0 by something. So this will never be 0. So there is no x-intercept. And then you could figure out the other side of this graph if you needed to, if you were graphing it, just by plugging in some values. Maybe you plug in 6. 6 minus 5 is 1. -3 over 1 is -3, so you know it's here. So the graph is going like this. I just want to point out that it's not always opposite like this. I know it keeps coming out like that, but sometimes this occurs here, and then the other side of the graph is here. And as long as you're on the other side of this vertical asymptote, they could both be going up, they could both be going down, or they could be opposite this way, or they could be opposite this way. Okay, you have to plug in a few points to determine that. One final example. Y equals, which one did I just do? 2x squared plus 6x over -4x squared plus 8x. You can factor out a 2x in the numerator, which gives you x plus 3. And you can factor out a 2x in the denominator, which gives you -2x plus 4. These, of course, cancel, and then it reduces to x plus 3. And in the denominator, I could factor out a -2 here, which gives me x minus 2. So this is reduced now. You can see in the original over here, I could not plug in a 2, because if x equals 2, I'd get -2 times 2 plus 4, which makes 0, and you can't have 0 in the denominator. Also, x can't equal 0 because 2 times 0 is 0, which would make this whole thing equal 0. So, but then when I reduce it, I still can't plug in x equals 2. So that's a vertical asymptote, a number that you absolutely cannot plug in, x equals 2. Horizontal asymptote, I go back and look at the original function. I can see that the exponents are the same in the numerator and denominator, so I look at the coefficient, which is -2 over 4, or -1/2. There's a hole. A hole is a value that I couldn't plug in, but now I can. So there's a hole at x equals 0, more specifically at 0, comma. So I plug in 0 into this function. 0 minus 2 is -2 times -2 is 4. 0 plus 3, so I get 3/4. There's a hole at 3/4. My y-intercept is when my x is 0. So I can just make x equals 0 here, which is what I just did here. So it happens to be 3/4. So my y-intercept is where the hole occurs. It's the same point. And then the x-intercept is when the y value is 0. And so this y, in order for this y to equal 0, the numerator would have to equal 0. And the way that's going to happen is if x is -3, because -3 plus 3 equals 0, and then this whole thing will equal 0. So it's at -3. And that's your x-intercept. And then you can graph that. Okay, I think I'm going to stop because I don't want it to be too long of a video. But that's the types of things I want you to be able to find: the vertical asymptote, the horizontal asymptote, the whole, the x-intercept, and the y-intercept.